A Diels-Alder reaction is a reaction between a conjugated diene and a dienophile. So you start with the conjugated diene, and the conjugated diene need to have the double bonds on the same side. So it needs to be in an S-cis conformation. And you're reacting this with a dienophile. The dienophile needs to have at least 1 degree of unsaturation. So it can be either an alkene or it can be an alkyne. Alkyne has 2 degrees of unsaturation. The reaction happens in presence of heat, and your product is always a cyclohexane where you are making a pi bond and 2 sigma bonds. This is going to be a concerted reaction. It is a one-step reaction, and the mechanism happens as follows. Diels-Alder reaction is like any organic reaction where a nucleophile reacts with an electrophile. The nucleophile is going to be the conjugated diene because this is our electron source in there. It is an electron source because it does have more double bonds than the dienophile. So the arrow is going to start from the nucleophile towards the electrophile in there. Let's go ahead and number our carbons. So that is going to be carbon 1, 2, 3, and 4. That is going to be carbon 5. This is going to be carbon 6. It doesn't matter if you have substituents between carbons 1 and 4 or 5 and 6, neglect them and only number the conjugated part of the molecule, which is supposed to be 4 carbons, and then the dienophile, which is supposed to be 2 carbons. So at the end, you should end up numbering 6 carbons in there so that your product is going to be a cyclohexane. After you draw your product, then you worry about the substituents and you put them wherever they belong. So your reaction is going to start from the nucleophile, precisely from the double bond between carbons 1 and 2. So the double bond between carbons 1 and 2 is going to break and open up and form a double bond between carbons 2 and 3. As we said, this is going to be a concerted reaction. Concerted reaction means it is a one-step reaction where bonds are broken and formed at the same time. So you have the double bond between 1 and 2 is broken to form a new double bond between carbons 2 and 3, and this is the new pi bond that is formed. And then you have the double bond between carbons 3 and 4 is going to break and form now a U bond between 4 and 5. And then you have the double bond between 5 and 6 is going to break and form a new bond between 6 and 1. So your product is going to always be a cyclohexane. Here I am representing the cyclohexane in its planar structure. It is better to represent it in its puckered conformation. And this is how you do it in the puckered cyclohexane conformation. For this reaction to happen, the diene is going to approach the dienophile. And imagine like those two are going to be on top of each other. The diene is going to be underneath the dienophile so that you will have the p orbital of this carbon overlapping with the p orbital of this carbon over here to make a sigma bond, because we know that sigma bonds are formed whenever you have an overlap of the orbitals in there. So to have an overlap of the orbitals, the double bonds, they need to be in an S-cis conformation. They cannot be in an S-trans conformation. So let's go ahead and explain. Why the dienes need to be in an S-cis conformation and not in an S-trans conformation. So we said that dienes are going to be our nucleophiles. If they are going to be our nucleophiles, then we need to pick the highest occupied molecular orbital for those dienes because it's this orbital that is filled with electrons. Since the nucleophile needs to be our electron source in there. The dienophile on the other end is going to be our electrophile. So for it to be our electrophile, it needs to be lacking electrons. So we're going to pick the lowest unoccupied molecular orbital. This is the frontier molecular orbitals, and this is how you draw them. And therefore, both the lowest unoccupied molecular orbital and the highest occupied molecular orbital in there for the diene. So in order to have a reaction in here, the diene is going to come and approach the dienophile. The diene is going to be at the top and the dienophile is going to be at the bottom. The reaction is going to be between carbons 1 and 6, because this is where you are forming the new sigma bond, and between carbons 4 and 5. So you are forming a sigma bond between those two. And to form a sigma bond, you need to have an overlap of the p orbitals between carbons 1 and 6. And as you can see, these two lobes are the same sign. They are both shaded. So you can form a bonding state between those two lobes in here, and you can form a bonding state between those two lobes in there. When they overlap with each other, they make a bonding state and they make a sigma bond. If carbon number 4, frontier orbital, which is the p orbital, is far away from 5, as in the S-trans conformation. So this is carbon 1, this is carbon 2, this is a 3, and this is 4. So 4 is far away from 5. Although 6 is close, so I can do bonding in here. But here it's too far away that the overlap is impossible. So this is why there will be no reaction if your diene has an S-trans conformation. You need to be able to rotate your diene to make it S-cis and then do the Diels-Alder reaction. If you are able to rotate it, then yes, there is a reaction in there. Like for example, in here, the double bonds, they are separated by a sigma bond. I can freely rotate, fix one carbon in here. So I'm fixing this carbon and I am rotating the carbon on the top. So rotate the carbon on the top, then it's going to be in. This is going to be an S-cis conformation. The reaction is going to happen. And it's going to happen by starting from the double bond between carbons 1 and 2 is going to open up, form a double bond between 2 and 3. The double bond between 3 and 4 is going to open up and form a new sigma bond between 4 and 5, and then a new sigma bond between 6 and 1, and I get my cyclohexane. On the other end, if the double bonds, they are locked in an S-trans conformation, there is no way that you can do a rotation in this case without breaking the sigma bond of the cycle. Then there will be no reaction because there will be no overlap between this carbon over here and this carbon over there. So this is why there will be no reaction. Now in this example over here, I'm starting with my diene and the dienophile. We said that the dienophile can either be an alkene or an alkyne. Here, my dienophile is an alkyne. Okay, so whenever you start numbering in this case, you're going to start numbering just the conjugated part. Forget about the substituents in there. And the dienophile, the carbons of the dienophile. So you should end up having 6 carbons at the end. Now let's start by doing the rotation of the S-trans to make it S-cis. Remember, when you do a rotation for these systems, the stereochemistry of the substituents around the double bond needs to be retained. Fix one double bond and rotate the other. Here I'm fixing this double bond. My substituents around the double bond are trans. I'm just going to keep them trans. This is going to force the CH3 to be out, off or away from the diene. And I'm going to rotate this double bond in here and make it S-cis with respect to the other double bond. This is also going to force the CH3 in here to be pointed away from the diene. So both of these CH3s are going to be pointed out. So this one is out and this one is out. Okay, both of those are out. still this is going to be my nucleophile, this is going to be my electrophile in there. So let's start our reaction over here by making a double bond between carbons 2 and 3, opening up the bond between 3 and 4, and making a bond between 4 and 5, and opening up just one pi bond between 5 and 6, and making a bond between 6 and 1. Notice here I only used one pi bond. So I'm going to end up having a double bond between carbons 5 and 6. Draw your cyclohexene in this case. Here in this case it's going to be the cyclohexadiene. And put your double bonds, your new double bonds between carbons 2 and 3, your existing double bond between 5 and 6. This is what remained from a triple bond. So with the triple bond, if you start with the dienophile triple bond, you're going to end up having a double bond between 5 and 6 in there. Now, the rule about the substituents. If your substituents are pointing away from the diene, both are out. Out means that you need to represent them or show them to be behind. So both of them are going to be behind in this case, and you put them on carbon 4 and carbon 1. So you take carbon 1, carbon 4, and you put your substituents in there. We have substituents on carbons 5 and 6 as well. Because the triple bond is linear, then the cyanides are going to appear on the same side in the product. And they are going to appear on the same side. We always prefer the cyanide whenever the triple bond approaches the diene. We always prefer that those substituents, they are pointed away from the double bond. So to show them pointed away from the double bond when the triple bond approaches the diene, we show them pointed down. Pointed down means that I am showing an endo product. So always make sure that the substituents on carbons 5 and 6 to be pointed down and showing the endo product, meaning that they need to be away from the system of the diene when the diene approaches the dienophile. This is called the endo product. The exo product is when the cyanides are pointed up, and this is close to the diene system when it approaches. This is unpreferred, so this is why we don't show it. We always show the substituents on carbons 5 and 6 if we can to be pointed down, and this is the endo product. So let's have another example in here. Always highlight your diene and your dienophile. Make your cyclohexene, and then put your substituents. Here we have substituents around carbon 1 and 4. We have a bridge of 2 carbons. Go ahead and put the bridge of 2 carbons. And then you have your substituents on carbon 6. That substituent on carbon 6, always make it an endo if you can. So since it's a one substituent in here, we're just going to make it pointing down, and that is going to be an endo. Here I'm showing you both products and both are acceptable. However, this one is more preferred to show it as a puppet conformation. For this example over here, highlight your diene and your dienophile. Now notice here that in my diene, I do have a substituent of 1 carbon between carbons 1 and 4. And I do have a substituent, this whole substituent in there between 5 and 6. I neglect them when I number. You go ahead and you draw your cyclohexene first. So go ahead and you draw your cyclohexene. Once you draw your cyclohexene, then go ahead and put your substituents in there. So I'm having a substituents between carbons 1 and 4, and this is a bridge of 1 carbon. So go ahead and make a bridge of 1 carbon in there. And then you have your substituents around carbon 5 and 6. This is going to be pointed down. This is the endo product in there. This is more preferred than the exo product. So let's consider the rule of the substituents on the diene when the substituents are on carbons 1 and 4 of the diene. So they are on carbons 1 and 4 of the diene. Okay, just when they are on carbons 1 and 4 of the diene. So over here, you are doing the rotation. And as I said, when you do the rotation, please make sure to retain the stereochemistry of the substituents around the double bond. If they are trans, keep them trans. In this case, both CH3s are going to be out. Out means that they should be behind. So trans-trans is going to give you a cis product. And by what I mean by cis product is the substituents on carbons 1 and 4, they are going to be cis with respect to each other. If you are starting with a trans cis or a cis trans diene, then in this case, do the rotation. And once you do the rotation, keep the same stereochemistry of the substituents. So here they are cis with respect to each other. So the CH3 is forced to be in, and the CH3 is forced to be out. So now this in means that the CH3 is going to be up, and the out means behind. So always the out means behind. So on carbons 1 and 4 now, the CH3 is going to be up. The CH3 here is going to be behind. So I'm going to end up getting trans substituents. It doesn't matter if I start with a trans cis or a cis trans. Let's say if I start with a cis diene. Here you go. So I'm starting here with a cis diene. So I'm going to go ahead and do a sigma bond rotation. And when I'm doing a sigma bond rotation, I'm just going to go ahead and fix this carbon over here and do the rotation of this carbon. Okay, so I'm going to end up getting both CH3s are going to be in. So this one is going to be in and this one is going to be in. So go ahead and number your carbons. This is going to be 4. Now, if I will react this with a dienophile, this is going to be 5. This is going to be 6. I'm going to get a cyclohexene. Here you go. And now my CH3s are going to be on the same side. So this is going to be in. This is going to be in. So both are going to be up. So the CH3 is going to be up, and this CH3 over here is going to be up. This is going to be my double bond in there, and this is going to be my product. Number your carbons in there. This is 4, this is 5, and this is 6. So as a summary, if you are starting with a cis diene, then you're going to end up getting the cis product. Okay, so these are the 3 rules that I want you to know. Starting from a trans diene, you're going to end up getting the cis product. And we're talking about the substituents on carbons 1 and 4 on the diene only. Okay, then there are going to be cis with respect to each other. If I'm starting with either trans cis or cis trans, then the substituents on carbons 1 and 4 are going to be trans with respect to each other. And if I'm starting with a cis diene, then the substituents on carbons 1 and 4 are going to be cis with respect to each other. You are not going to be responsible to show isomers, because when the diene approaches the dienophile, it can either approach the dienophile this way, or it can do the rotation and approach it this way. So you're going to end up getting a pair of enantiomers. So you can show either one of these products. You don't have to show both of them. Now, for the substituents on the dienophile, they have to retain the same stereochemistry. So if the substituents are on the same side, they need to remain on the same side. Something like this. So if they are on the same side, you need to show them on the same side in there. Whether you show them both up or whether you show them both down, you can pick whatever you want, although we prefer both to be down. And this is going to be the endo product. This is going to be more preferred than showing them both up. And if you have both of the substituents being on opposite sides, again, as I said, there is a difference with the approach of the diene to the dienophile. So the dienophile can rotate in this case, as you can see. So the R's can be in, out, or out, in. So this part here, you are not responsible for. What you are responsible for to know is when the substituents are on opposite side, then you need to show them on opposite side whenever you are drawing your product. So this is carbon 5, this is carbon 6, this is carbons 1, 2, 3, and 4. So on carbons 5 and 6, in this case, this is 5 and this is 6, the substituents need to be on opposite side. Whether they are one in front, the other behind, or the opposite in there, it really doesn't matter. Just pick one in there because both form, but you are not responsible for the stereochemistry. So just pick one of those and write it down. Although we prefer, as we said, that on carbon number 5, if you can make that group down, make it down, because this one is going to be our endo product, which is preferred. The last section of this topic is the type of the substituents on both the diene and the dienophile. So we've considered the stereochemistry of the substituents. Just to cap, we said that the substituents on the dienophile need to retain the stereochemistry. So if they are cis, they need to show cis around the carbons that they are on. So this is carbons 5 and 6, so they need to show cis. If they are trans, they need to show trans. Now on carbons 1 and 4, we have different types of stereochemistries in there. And we said that whenever they are both in, means that you need to show them in front. Out means that you need to show them behind. So this is what we said, and this is between carbons 1 and 4. Okay? Now, we said that whenever we started the reaction, that dienes are simply our nucleophiles, and dienophiles are our electrophiles. And this is how the reaction is driven by starting from the nucleophile, giving electrons, and then making a bond between 4 and 5, and then making a bond between 6 and 1 in there. So to make the diene more nucleophilic, you need to add electrons to it. To add electrons to it, you are going to place substituents on the diene to give electrons to the diene. And those substituents, we're going to call them donating groups, electron donating groups. We do have multiple examples of electron donating groups. So if you have an sp3 hybrid carbon, that sp3 hybrid carbon can donate electrons to the sp2 hybrid carbon by simple inductive effect. We've talked about inductive effect in organic 1. So you have an sp2 carbon versus an sp3 carbon in there. And we said that inductive effect is the pull of electrons through the sigma bond due to the difference in electronegativity. The sp2 is more electronegative than the sp3. So the sp2 is going to pull electrons from the sp3 in there. So now the CH3 is going to look as if it's donating electrons to the sp2. Donating electrons here, there is a double bond in there. So donating electrons here, it's going to increase the nucleophilicity of this double bond. It's going to make it more nucleophilic so the reaction can happen faster. Another example of an electron donating group is a heteroatom with a lone pair, like oxygen or nitrogen in there. This is going to donate electrons by resonance. This here donates electrons by inductive effect. There is no lone pairs. Here, since I have lone pairs, I can donate electrons by resonance. Donating electrons by resonance, again, is going to increase the nucleophilicity of this diene in there, make it more nucleophilic. And this is the whole idea for this reaction to proceed forward, the nucleophile needs to be more nucleophilic. The electrophile needs to be more electrophilic. So the electrophile needs to be electron deficient. To be electron deficient, you have to place on the double bonds, on the carbon of the double bonds, electron withdrawing groups. Those electron withdrawing groups are going to take electrons away from the double bonds. Taking electrons from the double bond is going to make that double bond in desperate need of electrons so that you can have a reaction between the nucleophile and the electrophile. These are examples of electron withdrawing groups. Any carbonyl, or in general, any carbon with a partial positive or a positive charge atom that is placed directly on the dienophile is going to withdraw electrons from the double bond and make the dienophile more electrophilic. So the more electron withdrawing group on the dienophile, the more reactive the dienophile is. So let's go ahead and rank the reactivity of the dienophiles. Let's start with the first three dienophiles in there. So let's highlight the dienophile. So this is going to be my alkene, the dienophile, and see how many electron withdrawing groups are there around the dienophile. The more electron withdrawing groups, the more reactive the dienophile is. So this dienophile has this partial positive carbon and this partial positive carbon. So it does have two electron withdrawing groups next to it. This one has one electron withdrawing group next to it. And this one over here has a CH2, two of them, and these are electron donating groups. Electron donating groups, they decrease the reactivity of the dienophile because electron donating groups gives electrons and you want a substituent on the dienophile to take electrons away from it to make it more electrophilic. So over here, the last structure is going to be the most reactive, and this one is going to be the least reactive. Okay, let's have another example over here. So locate your dienophile. Your dienophile has two carbons, sp3 hybrid carbons on it. These are both electron donating groups. The more electron donating groups, the less reactive the dienophile is. So we're expecting this one to be the least reactive because it does have two electron donating groups on it. This dienophile has one carbonyl next to it. So if I want to draw it, you need to be able to draw your esters, okay? So this is going to be an ester over here. This is partial positive carbon. This is an electron withdrawing group, and I have one electron withdrawing group around my dienophile. Here, I do have two electron withdrawing groups around my dienophile. I have two NO2s in there. So this is going to be an electron withdrawing group. This is going to be an electron withdrawing group. So this is going to be the most reactive. This is going to be the least reactive, and this is going to be in the middle. So again, dienophiles, to be reactive, to be more electrophilic, it needs to have electron withdrawing groups on it. The more, the better.